This is LeetCode's search and rotated sorted array, and the big hint here is that we need to get O of log n runtime complexity. Generally, when you're doing an array problem and they ask for log n runtime complexity, this means you need to do a binary search. The interesting thing here is that we have this weird pivot where we possibly could have one side of the array not be sorted perfectly, and therefore the binary search wouldn't work very well. Now I have the same array here that was pivoted in different amounts. And essentially there are three cases here. And in case one, the pivot initially is going to be on the right side. So here's the pivot, it goes from the larger number to the smaller number. For number two, the pivot is on the left side. And for number three, the pivot is where we are exactly. So we need an algorithm that works for all three of these cases. So if our target is 0, we're going to start out with our mid at 6. And we see 6 is not equal to 0. Now we need to cut the array in half by figuring out which side we need to check next. So in this case, we need to check 780. For our second case, if we're checking for 0, we need to check this 80 side. And for our third case, if we're checking for 4, we need to check the 456 side. Now the question is, how do we get an algorithm that does it in all cases? And there are some tricks you can do to make it simpler than this. But the way I like to think about it is we need to check which of these sides is perfectly sorted. So we know that in this case, 4 and 5 is perfectly sorted, but 7, 8, 0 is not sorted. We know in the second case, 8 and 0 is not sorted, but 5, 6, 7 is. And in the third case, both sides are actually perfectly sorted because we're on the pivot. Now, once we know which side is perfectly sorted, we can just check if the target is in that side. So in the first case, is target within 4 and 5? The answer is no. And therefore, we go and check the right side. In the second case, is the target of 0 in 5, 6, and 7? The answer is no, so we go and check the left side. And in the third case, is 4 within 4, 5, and 6? And the answer is yes, so we check the right side. Then we do the same exact algorithm, just on this array here. In this case, both sides are perfectly sorted, so it doesn't really matter. We just check, is it on the left side? No, so we check the right side of 0. And then that's our answer there. In this case, there is no really left side, so we just go to the right side. And in this case, both sides are sorted, and it's on the left side, so we just go to the left side. So that's the main idea. We do a binary search. We see which side is perfectly sorted. We check if the target is in that side. If it is, we go to that side. Otherwise, we go to the other side. And of course, if we're looking for a target that's not in the array at all, eventually we'll reach a point where we just get to an array of one element. And if that element does not equal the target, we just return -1. So this is an O of log n runtime complexity algorithm, and an O of 1 space-time complexity algorithm, because we're not really storing anything, we're just storing some variables. Now, before we get to the code, if you found that helpful so far, please give a like and a subscribe, because it really helps the YouTube algorithm. And let's get to the code. Okay, first let's set our left to be 0, and our right is length of nums -1, and we're going to do a while true loop here. So our mid is equal to the left plus the right divided by 2. And first we check if nums at mid equals target. If it is, we return mid because we found our element. And let's also add the condition here where if left is equal to right, then we break. And at the very end of the function, we're going to return -1. In this way, we'll avoid infinite loops. Okay, now we need to get which side is perfectly sorted. So if nums at left is less than or equal to nums at mid -1. So if that's true, that means the left side is sorted. Then if nums at left is less than or equal to target, and if target is less than or equal to nums at mid -1, we know the left side contains our target. So we want to set right to be equal to mid -1, so we only look at the left side now. Else, we want to only look at the right side, so we make left equal to mid +1. Now, if the left side is not sorted, that must mean the right side is sorted. So now we do the same thing, but we're going to be checking the right side. So if the right side contains the target, that must mean we want to check the right side more. So we're going to increase left. Else, we need to decrease right and check the left side. Now, there is one issue here. And that's if mid is equal to left, that means that mid -1 is going to be less than left. And for example, if they're both 0, then we're going to be checking a -1 here. That's clearly wrong. So what we need to do is get left of mid, which is going to equal the maximum of mid -1 and left. So left of mid will, at the very worst case, equal left. Otherwise, it'll be mid -1. And we need to use that here and here. And we need to do the same thing with the right side. So right of mid is equal to the minimum of mid +1 and right. So same exact idea, except we just use it for the right side. And so instead of mid plus 1 here, we do right of mid. And that's it. And we got a run time of 20 milliseconds, which is faster than 98% of Python online submissions. Now, there might be a way to do this in a slightly more concise manner, but I think this makes the most sense and is easy to follow. So with that said, if you found this video helpful, please give a like and a subscribe, and I'll see you next time.